let's take a really simple example where we have just a function f of x, and it's equal to itself. It's equal to x. So take this function. Is this function homogeneous? Okay, what's the degree of its degree? 1, yeah. So if we multiply x times b, it's equal to b times the original function, and it's just b raised to the first power. So it's homogeneous degree 1. Okay, what about this one? Is this one homogeneous? Okay, no, why not? If we multiply x times b, the resulting function is not just b, some power b times the original function. This constant a here messes things up as long as a isn't 0, of course. Okay, good. How about this one here? Alpha 1 raised to the x1 raised to the alpha, x2 raised to the beta. Homogeneous or not? Okay, yes, it is. It probably might be worth demonstrating that one. So in this case, we have a function, or I'm calling this f, aren't I? So f of x1, x2 is equal to alpha 1, or sorry, x1 to the alpha, x2 to the beta. If I multiply both these things times b, then I have f of b x1, b x2 equal to b x1 to the alpha, b x2 to the beta. That, of course, is equal to b to the alpha times b to the beta times x1 to the alpha, x2 to the beta. So this is equal to b to the alpha plus beta, all times the original function, f of x1, x2. And so this function is homogeneous of degree alpha plus beta. So notice the degree doesn't have to be integer. Alpha plus beta could be 1/2 and 1/3 or something like that. Okay, good. All right. Any quick views on this one? Homogeneous or not homogeneous? If I multiply, who votes for homogeneous? Okay, some of you who votes are not homogeneous. Okay, a roughly equal number of you are uncommitted. That's okay. Let's go through the same exercise here. So we've got f of x1, x2 here equal to alpha log x1 plus beta log x2. That's some notation I'm using? Yes. Okay, so same idea. We multiply the x's times b. So we have f of b x1, b x2 equal to alpha log of, b x1 plus beta log b x2. Using the rule of logs, how many log b's do I wind up with? Well, 2. No, well, no, not 2. Yeah, alpha plus beta of them. So I wind up with alpha plus beta log b plus the original function, f of x1, x2. Okay, so now we've written it this way. It's a constant plus the original f. So this is not a homogeneous function. We're not scaling it up by multiplication. Instead, we're adding a constant to it. Okay. Oh, here's a good one. How about this one? Homogeneous or not? Who votes for yes? Okay, who votes for no? Okay, so one of the yes people. You're a yes person. You want a yes person? Who's a yes person? You're a yes person. I heard yeses over here. Who said yes? Admit, confess. You thought yes. Okay, tell us why it's homogeneous. Tell us why it's homogeneous. Okay, that's probably. I mean, actually, you could do it that way. This is actually a special case of this, where alpha is equal to 1 and beta is equal to -1. So that's one way to do it. Another really immediate way to see it is, well, gee, if you multiply the x1 by b and x2 by b, the b's immediately cancel, and so you get back the original function. So this one's homogeneous of what degree? Of degree 0, exactly. Okay, very good. So that's a definition and some examples of homogeneous functions. Let me tell you quickly about a generalization of homogeneous functions. Okay, and the generalization is called homotheticity. So we say that a function f of x1, x2 is homothetic if there exists a monotonic transformation of the function such that the monotonic transformation is homogeneous. That's the definition. And I know this is getting complicated. It won't get more complicated after this, I promise. So the question is, does there exist a monotonic transformation, big F? So you apply the monotonic transformation to the function and get a homogeneous function. That's the question. If there is such a transformation and if the result is homogeneous, then we say the function is homothetic. Okay, quick question. Is this one homothetic? F of x equal to x? Yes, why? It's trivially homothetic because we already know it's homogeneous. So you can apply a trivial transformation of just taking itself, and it's homogeneous, so you're done. Good. Okay, what about this one? This one was, remember, not homogeneous. F of x equal to a plus x was not homogeneous. Is it homothetic? Is there a monotonic transformation we can apply to this that is homogeneous? Very good. So Hillary says add minus a. That is a monotonic transformation. It's an increasing function. If we add minus a, we get back x. We already know that's homogeneous. Done. So that is a homothetic function. That's quite correct. Okay. This one before. So this alpha times log x1 plus beta log x2. We showed a moment ago that was not homogeneous. Is it homothetic? Who says yes? Yeah, very good. So we already know that this thing is homogeneous, and this thing is just, you just take the exponentiation of that thing. That's the transformation you need. If you take e to all this stuff, you get back that homogeneous function. So it's homothetic. Okay, how about this bottom line here? I guess I give you the answer away. It's not homothetic if you read the following line. So it's not homothetic because if we multiply x1, we still have a funny constant out here that screws things up. This function is quasi-homothetic. I might come back to that later. I'm not going to trouble you with that further right now. Okay, so now I want to briefly, it's taking longer than I expected, but I want to tell you briefly about indirect utility. Okay, so I already introduced indirect utility, or motivated it, by saying that indirect utility function was the answer to the question of how much a consumer facing prices P1 and P2 values income Y. Okay, so there's an easy way to get the indirect utility function. It's to say, well, gee, if you have a utility function defined over consumptions of goods x1 and x2, then what we can do is figure out, and you face a budget constraint, given income Y, what you can do is figure out your Marshallian demands. So Marshallian demands tell us how much you'll consume of good x1 and x2 given prices and income, and just plug those Marshallian demands, plug that solution into the utility function. And so I had to start off with the utility function u of x1, x2. I plug in the Marshallian demands, which are the solutions to the consumer problem. Now I have a function which depends not on x1 and x2 directly, but instead indirectly on prices and on income. And I'm going to call that function v. So this v is the value function or the indirect utility function for the consumer. And it tells us, for a consumer facing prices p with income y, it tells us how happy they are, what their utility is. Is that clear? So we know consumer's utility function, we know they have income y, we know they face functions p. V tells us in a direct way, the indirect utility function tells us in a direct way how much utility they get, given the resources they've got, given the preferences they have, and given the prices they face. Okay, so let me go through, let me extend the example we started with earlier. We got some Marshallian demands for a consumer with this kind of logarithmic Cobb-Douglas utility. I'm going to go ahead and extend this, and we're going to work out what their indirect utility function is. So everyone ready? Any questions before I go on? Okay, here we go. So I said a moment ago that we could just plug in the solutions x1 and x2 from this consumer problem, maximizing your utility subject to a budget constraint. We can also write it this way. The indirect utility function is equal to the maximal value of the utility function given the solution to this maximization problem. So this is another way to write this thing. The solution here we're going to call x1, sorry, the star should be up above that. So we'll call the solution x1 star of prices and income. These are the Marshallian demands. We already did that. We solved the Marshallian demands for an example earlier today. And this is what I just said a moment ago. The indirect utility function depends on prices and income, and we just plug in the Marshallian solution to this problem to figure out what v is. Okay, so we're coming back to our example here. So let's let the utility function be 1/2 log x1 plus 1/2 log x2. This is a special case of what we did before, where we're taking alpha equal to what? Alpha equal to 1/2. Okay. The marginal utility here is going to be useful to have. The marginal utility of good x1 or good x2, they're the same, is just equal to 1 over 2 times the quantity of the good. That's the marginal utility for the consumer. So notice as x1 or as xi increases, marginal utility falls. There's decreasing marginal utility for the consumer. Okay. So I'm going to use this. We talked earlier about how at the optimum the consumer sets the marginal rate of substitution equal to the ratio of prices. I'm just going to do that here. The marginal rate of substitution is equal to the ratio of marginal utilities, and at the optimum that's going to be equal to the ratio of prices. I'm going to substitute in this expression for the marginal utility for good 1 and good 2 into here, and I wind up with this incredibly simple expression that tells me that at the optimum the consumer is going to set the ratio of x2 to x1 equal to the ratio of prices p1 over p2. So this is going to characterize the solution. Using the same, I talked a little bit ago about isonclines. The isocline for this consumer just looks like this. We can have x1, x2, and what this tells us is that the ratio of those things is going to have a fixed slope. So x2 over x1 is going to have a fixed slope like this with a slope of p1 over p2. So these are isoclines. This is going to pick off the points of intersect, or the points of tangency between the budget lines and the indifference curves. And for these references, it'll be a straight line. Okay. All right. So that's going to have to be satisfied at the optimum. What's the other thing that has to be satisfied at the optimum for this consumer? The budget constraint, exactly. So this equation we've got here, this x2 over x1 equal to ratios of prices, tells us the rate at which the consumer is willing to trade x1 and x2, but we haven't used the constraint yet. The constraint comes from the budget constraint in this case. So we use the budget constraint to pin down one of these indifference curves. We want to have a solution like this. And so these points are like these x1 stars, x2 stars we defined on the previous slide. Okay, so what do we get? Well, here's how you can go, if we want to go through the algebra, here's how you can do it. You can define x2 in terms of x1. That's just this curve I drew. That's the isocline. We combine that. We plug that into the budget constraint. Solve for x1. We get y over 2 times p1 as the solution for the Marshallian demand for good 1. And we get y over 2p2 as the solution for the Marshallian demand for good 2. So this is again just a special case of what we already solved several times now, 2 or 3 times at least. Okay, so this is the Marshallian demands. Now we're going to take the next step. This is why we're interested in this example. We're going to take this solution and plug it back into the utility function to get the indirect utility function. So that'll tell us how happy a consumer is if they have income y and face prices p1 and p2. Okay, so here's the trick. Here's our original utility function. It involves this half log x1. So I'm just plugging in this expression. This is the solution for x1 plus 1/2 log x2. Plug in there. And so this is the indirect utility function. We can rearrange it and make it a little bit nicer, again using sort of log tricks. And we find that for this example, the indirect utility function is equal to the log of y minus 1/2 the log of p1 minus the log 1/2 the log of p2, and then minus a little constant at the end. Okay. So that's kind of nice. What happens to this person's happiness as their income increases? The income increases. At what rate does so? I heard the answer goes up. At what rate does it go up? So it goes up at a logarithmic rate. So as income increases, this person has a utility function which does something like that. So it's just this is the log of y plus some constant. Okay. So notice this is increasing. So that comes from non-satiation. This person gets happier as they get more income. But because it's concave down, they get happier at a decreasing rate. Like the Beatles, once you have a lot of income, you value an additional dollar less. All right. Okay. What about this thing about prices? What happens to indirect utility as a function of prices? So let's say the P1 goes up. It makes perfect sense. If the price of one of the goods that you value increases, you're less happy because you can afford to buy less of it. Okay? So if prices go up, whether it's P1 or P2, your indirect utility function falls. So you're happier with more income, you're less happy with high prices, and that's sort of all captured here by this indirect utility function. Okay. I think I have good timing for the end here because I want to take a few minutes. So before you run out the door, either in delight or confusion or any other way, make sure to come up front here. We're going to put a sheet of paper. Actually, you can file around this side. Put a sheet of paper here. I want you to sign your name on it as you perform the act of turning in your expenditure diary. Oh, there's 2 important things I wanted to say about the expenditure diary that I neglected to say at the beginning of class. The first of those 2 things is this. If you turn in your expenditure diary today, you'll get 2 extra credit points that we'll use to augment your problem set grade for the course. That's the first thing. The second thing is this. If you forgot your expenditure diary, or it's not quite finished, or whatever, then if you can turn it in this week, I will give you 1 extra credit point. So in either case, you should see Jeff. Thank you.